Now we are going to study electric potential and potential energy due to a point charge. Now electric potential is the change in electric potential is defined by this expression, where this potential delta V means VB minus VA. Now when we are talking about a point charge, let us say we have a point charge Q which has a charge of Q, and we are moving from one point A to another point. Suppose it's somewhere here, B. So the unit vector, the vector from this charge, this will be RA vector, and the vector from this point will be RB vector. Now let's say that we are moving along a path which is somewhat like this, okay, and this is some distance. This point lies at some distance R vector from the charge. Now as you all know that the electric field due to any point charge, if it is positively charged, it will always be away from the charge. So if it is a positive charge and at this point we have to find out the direction of electric field, it will be away from the charge. So this will be the direction of electric field at this point. And displacement, now this displacement ds, it means that we're moving now, in this case we're moving from A to B, and at this particular point the displacement vector will be a tangent at that point. So let us say this is the displacement vector at this particular point. If you remember, the displacement vector on a circular path is a tangent to the path. If you're moving along this circle, the displacement vector will be a tangent at each point. Okay, so similar manner, the displacement vector at this point will be a tangent to this. And let us say that this angle is theta. So now we have to find out E vector dot. Let us find out E vector dot ds vector. So it will be E vector dot ds vector will be E ds cosine of theta, the angle between electric field and displacement vector. So it will be E ds and cosine theta. Okay, so I've written it again, cosine theta. Now in this triangle, if I draw a perpendicular on this line, then this angle, it will be a perpendicular, okay, and this distance, now if this is r, this distance should be dr in magnitude. So if I have to draw this triangle separately, it will look something like this. So this will be ds vector and magnitude, this will be dr vector magnitude, this angle is theta. So if you have to find out what is the value of cosine theta, it will be dr upon ds. So dr will be equal to ds cosine of theta. So we can replace this term and what we'll get is E dr. So this equation becomes VB minus VA will be equal to integral, because we are moving from A to B, so the total integration will be from A to B and EdR. So now because it is a point charge, and because of the point charge at each point, the electric field depends upon R. So when we are working with the point charge, the electric field is given by Keq upon R square. Okay. So let us use this expression here and it will be minus integral of KEQ upon R square dr, and we are integrating it from A to B. So this integration will turn out to be R minus 2 plus 1 divided by minus 2 plus 1 integrating from A to B. So it will be minus KQ minus 1 upon R to B, which could also be written as RA. So the total expression will be VP minus VA will be equal to RB minus RA. So this will be the potential difference about a point charge when we are moving from a point A to B. Now suppose that instead of moving from A to B, let us say that you're moving from an infinite point to any point B. So it means that A will be at infinity. So V infinity will be equal to 0 and 1 upon RA will be 1 upon R infinity will also be equal to 0. So you're moving from an infinite distance to point B. Then so this equation will turn out to be Vp will be equal to KEQ upon RB. Okay, so we can generalize this expression because we have B here and B here. So in general we can say that potential at any point will be equal to KEQ upon R, and R will be the distance from that point charge. So the potential from a point charge depends on R, and it is a scalar quantity. So whenever we'll be solving problems based on this, we will not care about the direction. While do not confuse it with this expression, which is the expression for electric field. The only difference between these two expressions is that the electric field is dependent on the second power of R, and here potential is dependent on the first power of R, inversely dependent. Okay. Now suppose that you have any charge. So what we get is that if you have any charge, suppose if it is plus Q, and at any point R, if you have to find out what is the electric potential, then at this point the potential will be KEQ upon R due to this charge Q, which is here. Now suppose that you have some charge which is Q1. So if this charge is Q1, then this potential due to this charge will be V1 and the charge will be Q1. Also, if there is any charge Q2, then at this point the potential will be KEQ2 upon. Now this distance R, suppose it is R12, so we say it is R12. Now suppose that we're moving some charge, let us say Q1, from an infinite distance to this point. Okay, so this charge Q1 is at some infinite distance, and so we are moving from infinity to R12. Now you know that the potential energy per unit charge is equal to the potential. So the potential energy will be at this point when we are bringing this charge. So it will be the test charge Q1 is being brought in this potential, which is V2. So potential energy will be V2 into Q1. So from here you can say that this V2 into Q1, and the potential at point, let's say this point is A, is given by KE Q2 upon R12 into Q1. So if you have two positive charges, Q1 and Q2, and they are at a certain distance R12 apart, then the potential energy between these two charges will be given by this expression. So this potential energy will depend on these charges. If these charges are oppositely charged, if suppose Q1 is a positive charge and Q2 is a negative charge, then the potential energy will be minus KE Q1 Q2 upon R12. So it will be a negative quantity. And if you have many charges, suppose it is Q1, Q2, Q3, R12, R23, R31. So you just have to add. So let us say it is U1, U2, U3. So the total potential energy will be U1 plus U2 plus U3, which can also be written as KE Q1 Q2 upon R12 plus KE Q2 Q3 upon R23 plus KE Q3 Q1 upon R13 or 31. Okay, so this will be the total energy of this system.